He's a veteran with over 30 years' experience working with computers large, small, and tiny. He still has a Sinclair ZX81 somewhere. He's part of the BBC Microbit team, where designed the Microbit's Bluetooth profile. He's a developer, cyclist, climber, photographer, and live music fan, and he's the technical program manager EMEA at Bluetooth SIG. Please welcome to the stage Mr. Martin Woolley.
Hi everyone. Well, I survived the opening pyrotechnics, so I call that a success already, which is good. So I'm Martin, so I work for the Bluetooth SIG. We are the standards body behind Bluetooth technology. Now, back in the 1990s, there were 1 billion devices connected to the internet, a big number. But only 10 years later, that had doubled to 2 billion, largely thanks to smartphones. The forecast for 2021, though, is staggering. It's that 48 billion devices will be connected to the internet, and 30% of those devices will be Bluetooth devices. Now, this is no coincidence. Bluetooth has been systematically developed over the years to keep pace with market requirements and to enable new things, and it's become a key enabler of the Internet of Things. If we reflect briefly on the way that Bluetooth has evolved, in the beginning, it was a cable replacement technology, and it gave us wireless mice and keyboards and some great audio solutions. Wind the clock forward, though, to about 2020, and Bluetooth Low Energy was released, and Bluetooth Low Energy is in pretty much every smartphone and tablet on the planet, and it gave rise to all sorts of medical devices, health and fitness devices, wearable technology, and so on. Later this year, to give you a sneak preview, in the summer, we're going to release a global industry standard for Bluetooth mesh networking. That's going to be a revolutionary release from the Bluetooth SIG, so watch out for that. More recently, though, Bluetooth 5 was released. Bluetooth 5 was released right at the very end of last year in December, and that's what I'm going to talk about today. And the headline changes we made were that we made it twice as fast, we increased the range by a factor of 4, and the capacity for broadcasting data we increased by a factor of 8. So I'm going to talk to you about those things in about 10 minutes flat right now. Let's start with speed. Bluetooth Low Energy is actually quite fast anyway, relative to other low-power wireless technologies. They tend to be limited to something like 250 kbps per second. Bluetooth version 4 already has 1 megabit per second as a speed of communication. So we doubled that to 2 megabits per second. Importantly, though, we made that speed selectable, so developers can switch from normal speed to high speed and back again, and so on. And the reason we did that is that there are use cases where faster data rates are important or helpful. Medical devices, health and fitness devices, they're measuring more and more dimensions of the human body, collecting more data. There are things out there we call buffered sensors. Think about your Fitbit activity trackers. They collect data from the environment, but they store it. They aggregate that data, they accumulate it, and then they transmit it all in one go later on. So they need faster data rates. And last but not least, there's the question of firmware. We all care about the Internet of Things. I don't want to get fried. I'm going to step back. We all want the Internet of Things to be secure. So keeping firmware up to date on devices is one of the ways that we can accomplish that. And firmware updates can be large. Doing them faster is a good thing. So Bluetooth, of course, is a radio technology, and we talk about symbol rates in the world of radio because it's analog, not digital. So what we really did here was we doubled the symbol rate. A symbol kind of represents a bit in the digital world. One of the consequences of this, now in Britain, we like to say there is no such thing as a free lunch. There's always a cost, okay, a hidden cost. So we can switch to 2 megabits per second rate. We can go faster for certain use cases, but one of the costs is that you get reduced range. Range is only 80% of the range that you'd get if you were doing the 1 megabit per second speed supported by Bluetooth version 4. Let's talk about range. So, first of all, we quadrupled the range of Bluetooth Low Energy. Why on earth did we do this? Because Bluetooth version 4 has a phenomenal range already. People, if I had time, I'd ask you what you think the range was, but I don't. There are modules on the market for Bluetooth version 4 that have a range of 500 meters. That's pretty substantial for a low-power wireless communications technology. I've already seen demonstrations of Bluetooth 5 achieving a range of well over 1 kilometer. This is staggering. It's not the 10 meters or 20 meters that people think. So why did we do it? Well, we were thinking about all sorts of things, but certainly the smart home, smart buildings was part of the equation, and industrial IoT. So coverage of whole buildings, the ability to pass through barriers and walls and still reach the perimeter of certain spaces, that's what we were thinking about. So now we have a range that's over 1 kilometer. But let's take a reality check and think about what we were really trying to do here and how we were constrained, because this is Bluetooth low energy and power consumption is key. It's one of the great benefits of the technology. So our job was to increase the effective range of Bluetooth by a factor of 4, but do it without increasing the transmission power. We could have cranked up the power, it would have gone further, but we can't do that because it's Bluetooth low energy. So the question arises, how on earth did we do this seemingly impossible task? And the answer is, we used magic, obviously. We hired this guy, he's now working as a consultant, he's very expensive, but he's very good and he helped us. In actual fact, and thank you, the person who laughed, I appreciate that. The magic that he helped us use, in fact, is called mathematics. So we use some mathematical techniques to make the receiving end of the communication more sensitive. And to understand the problem of range in wireless communications technology, you have to think about errors in communication. The way it works is that the transmitter transmits a signal, and the further away from the transmitter the receiver is, the weaker the signal is measured to be. And all around us, there's background noise that is at a certain level. And the closer our transmitted signal gets to that background noise, the more difficult it becomes to decode the information inside the radio. And at some point, we start to get errors. A transmitted one gets converted to a 0, it's wrong, and so on. And at some point, we get so many errors, we have to say, it doesn't work, we've reached the limit of our range. Okay? And that limit is defined in the specification. So all about errors. 2 ways of thinking about errors. Communications technology tends to always have something relating to error detection. So this has been the case for many decades. Paper tape, for example, used parity bits to allow you to check for read errors. Bluetooth version 4 uses cyclic redundancy checks. It can check whether or not what was received was what was transmitted. But it can't do any more than ask the transmitter to send the data again. So that's a very common strategy. Bluetooth version 5 uses an error correction scheme. This is much smarter, based upon mathematics, and allows the receiver to say, hey, this is wrong, but I know what you meant. So it can dynamically fix errors. And this allows us to work at a much lower signal-to-noise ratio, and therefore be much further away from the transmitter. So this is a picture of our problem. The black line is the error limit, and we reach that limit at a certain distance from the transmitter. With what's called forward error correction, the mathematical scheme we're using, we get to go much further away and we don't encounter that maximum error rate until we're at a much further distance from the transmitter and a much lower signal strength. So that's how the magic was achieved. It was all about maths. The next speaker is going to talk about maths as well. So let's talk about the third of the major Bluetooth 5 improvements. This is about something called broadcast message capacity. Now, to appreciate this, be aware that you can use Bluetooth devices in 2 ways. They can either connect to each other and exchange data over a connection, or they can work in a connectionless way, with one device just broadcasting data that any other device can see. Bluetooth beacons work like that. Who knows what a beacon is? Lots of you. Okay, so that's how they work. They just broadcast data. Beacons are a prime use case for the application of this broadcasting capability, and the numbers are really interesting. Over the last couple of years, we've shifted from companies running small pilots to rolling out serious deployments of beacons into their businesses. And the forecasts are amazing. These numbers are for individual years. This is not cumulative. By 2021, my favorite year in the future, the estimate is that there will be more than 500 million beacons shipped in that 1 year alone. This is a really important use case. They're going to be everywhere and inside all sorts of things. So Bluetooth version 4 kind of gave us generation 1 of the Bluetooth beacon. And version 4, broadcasting, we call it advertising, the packets are very small. A total of 31 bytes of data can be broadcast at a time, tiny amount of data, either a unique ID or a URL. So single purpose, very effective, very simple, but not sophisticated. Bluetooth version 5 gives us packets which are 8 times bigger, so physical things can say a lot more about themselves because they have more data with which to express their current state. I've depicted a fridge there for some reason, but it could be anything. So instead of just saying, I'm here, my fridge is now able to broadcast lots of information about itself, such as its temperature, how many times the door has been opened, any maintenance indicators, and so on. So this has all sorts of applications in all sorts of fields. So let me explain roughly how this works then. In the world of Bluetooth version 4, we're using radio, of course, because Bluetooth is a radio technology. Most low-power radio technologies use a single frequency, which does not scale. It can't scale. This is physics. Bluetooth uses 40 different frequencies. For broadcast purposes, it uses 3 specific ones. When we're connected, it uses the other 37 in a random fashion called frequency hopping, which makes it work really well in busy radio environments, and this stuff matters for the future too. For broadcasting, my current topic though, Bluetooth 4 does this. It broadcasts the same packet, first on advertising channel 1, it's actually channel 37, then on 38, 39, and we go round in a circle. The way Bluetooth 5 now does it is it splits the header part, which is my light blue color, it's only 6 bytes of data, from the main payload, which is now much larger. The header continues to be broadcast on our 3 special channels, but the payload uses one of those other 37 channels. And if you're thinking, I don't care about all this radio stuff, if you're involved in IoT and care about wireless, then trust me, you do. And I'll explain why later on. So we get to say much more, and we radically use the radio in a different way. If the 255 bytes is not enough for you, don't worry. You can take a large data set describing your thing or the environment it's in. You can split it into sections, and you can chain those sections together. So you can broadcast very large amounts of data now in a way that allows the receiver to reassemble the entire data set. So you can say an awful lot. So that was about the functional underlying technical aspect of this change. Let me just explain a couple of benefits, something I just referred to. We live in a world where the rules of physics apply, okay? It's tempting to think that it's all very abstract and the way we design our code is the way the world is. Well, ultimately, physics might disagree with you. And one of the issues with all wireless communications technologies is that radio is a resource which is finite. It has a finite capacity. If you don't use it in an intelligent way, you're going to run out of that capacity and things will stop working or start to work badly with things like packets colliding in midair and so on. So in the world of Bluetooth 4, again, we were using our special channels of 37, then 38, then 39, and broadcasting the same data on each of those channels one at a time. Now we're offloading most of our data onto one of 37 other radio frequencies. So our popular and important broadcast channels are much less used. We're only broadcasting 6 bytes at a time. So we're opening up lots of capacity for those special radio channels. And again, I'll reinforce that with my last slide. The other thing we're doing is we're deduplicating. With Bluetooth 4, we used to broadcast the same data on channels 37, then 38, then 39. Now we only broadcast the payload once. So we're using the radio less, which helps with power consumption, and we're using the radio spectrum less, which helps with scalability for the IoT. Gartner made a forecast, I think it's a couple of years ago now, that the typical home will contain 500 connected devices by, I think, 2021 again, that favorite year we all seem to like. 500 devices is an enormous number of devices in a small environment. A large proportion of those devices will be wireless. Without this kind of thinking, the 500 devices in a small space will not work because it won't scale. Think of Wi-Fi uses one frequency. Think about that. You've probably had problems with your neighbor's Wi-Fi interfering with yours. This is what this is all about. It's about enabling scalability for the IoT. So Bluetooth 5 is more than a minor change. It's a step up from Bluetooth 4, a significant improvement, and hopefully I've explained it in such a way that you can see it continues to be a key enabler for the Internet of Things. Thank you for listening.